Hello, my name is Noah Kamakam, and for my experiment, I'm investigating the effect of pH on the ability of P. porifera to filter nickel sulfate from seawater. P. porifera, more commonly known as sea sponges, are widely regarded as the filters of the ocean due to their ability to filter very large amounts of water in relation to their mass, anywhere from 2 to 20 cubic meters of water per kilogram of body weight. As seen in the diagram on the right here, sponges have small pores within them that allow phytoplankton to enter so that they can get their food, as sponges don't have mouths. However, as a byproduct, pollutants and heavy metals in specific can enter these pores and get trapped in these crevices you see, and that is how they gain their filtration ability and how the water around them is filtered. Acidification is a process in which atmospheric carbon dioxide enters the ocean and lowers the pH due to the creation of carbonic acid. Over the next century, the pH of the ocean is expected to drop from 8.1 to 7.6 as a result of ocean acidification. This was said by the European Environmental Agency. Research indicates that this drop in pH results in tissue loss and an overall decline in health for both sea sponges and other marine life. However, little research has been done into how this affects the ability of a sea sponge to filter water, specifically seawater containing heavy metals such as nickel, as a fluctuation in how much water is filtered could have drastic effects on sea life as a whole. The study by T. Bates and J. Bell in 2017 investigated how this drop in pH caused by ocean acidification affects the health and degradation of sponges. And they found that in two groups that sponges in a pH of 8.0 and sponges at a pH of 7.6, and the sponges in the pH of 7.6 had a significant increase in tissue degradation in comparison with the other sponges. And a study by J. Selvin et al. In 2007 found that just P. porifera have the ability to filter heavy metals from water. So I wanted to combine these two studies and see how the ability of sea sponges to filter heavy metals such as nickel sulfate from seawater is affected by the environment caused by ocean acidification, that being a lower pH. To do this, two separate tanks have been set up to hold one sponge each, as seen on the right, the top one being the sponge in the pH of 7.6, the bottom one being the sponge in the pH of 8.2. The tanks are identical in the water pump used, and therefore the water flow to each sponge. They are identical in food, as 5 milliliters of phytoplankton are added to each tank every Monday, Wednesday, and Friday. They both contain 6.4 liters of water and began with the same concentration of nickel sulfate hexahydrate, that being a 0.01 molarity solution. They are also equal in salinity, as the same amount of instant ocean sea salt mixture was added to both tanks. The only difference between the two environments is the pH. Both of the water pumps are shooting water directly into the sponges to ensure they get the same amount of water / nickel sulfate pumped into them every single day to make sure that the results are reliable. These little black cubes here are just for support for the sea sponges to make sure they don't go flying all over the place. To begin, the pH is measured and adjusted every Monday and Thursday using a pH meter to maintain the conditions the sponges are subjected to. To adjust pH, C-Chem alkaline buffer and acid buffer are added to their respective tanks. To measure the change in concentration of nickel sulfate over time, the absorbance value will be tested using a UV visible spectrophotometer every Monday, Wednesday, and Friday. Those absorbance values will then be converted into concentration values using the Beer-Lambert's law, in which the two are proportional to one another. So far, multiple Beer's law trials have been completed to ensure the proportionality between the concentration values and absorbance values tested. As you can see down here, these are the results of my Beer-Lambert's law experiment. I found the correlation between the two, and I came up with an equation up here in an R-squared value of 0.9997. And this equation I use when I get the absorbance values to convert them into concentration values, so I know exactly how much nickel sulfate has been filtered out of both tanks. I also came across the wavelength of 394 nanometers as I cross-referenced what I found along with studies online and determined that this was the peak absorbance for nickel sulfate, which is why I'm testing it at that value. And as I mentioned, 5 milliliters of phytoplankton are added to both tanks every Monday, Wednesday, and Friday. Results of my experiment, as seen here, there is a significant difference between how much nickel sulfate has been filtered by the two sponges. The green line represents the sponges in the tank of 7.6, and the purple line represents the sponges in the tank of 8.2 pH. Be seen here, the sponges have been filtering nickel sulfate out of the tanks at a relatively constant rate over the course of the 4 weeks of the experiment, and they've just been filtering normally. However, the sponge in the pH of 7.6 actually stagnated for around 2 weeks at around 0.048 absorbance value, and then as of recently, over the past week or two, that value has started to increase. I have hypotheses for why this is happening. However, it's something I need to look into in the future and find out why the absorbance is actually increasing instead of decreasing. The implications of the study, I hope to better understand how the process of ocean acidification affects the degradation of the outer layer of the sponge and therefore how its filtration ability is subsequently affected. I also believe the findings from this experiment can be used to predict how ocean acidification will affect other forms of sea life, specifically life with a similar structure to sponges such as corals. I also hope to use the study as a warning to the future to see how ocean acidification may impact how the ocean is filtered in the next century.